dear students, welcome back to 60 out of 60 in KCET Chemistry 2025 series in just 200 days. So yes, now we are doing the structure of atom chapter, okay, the second chapter of PU1, and in today's class we are going to discuss about the Bohr's model, okay. So this is the, I can say, most important topic from where the questions have been asked repeatedly. So yes, now and one more request here, please join our WhatsApp channel. The link of the WhatsApp channel will be there in the description section, and all access to the class notes, mock tests, solutions, everything is available in our WhatsApp channel, okay. So please join it. And now moving towards the today's class, so we have already discussed like how we are going to develop complete this lectures. So in part 1 we have already completed the discovery of subatomic particles, in which we discussed about the discovery of electrons, protons and neutrons, right. And after that we talked about the atomic models, and here we discussed about the Thomson model and the Rutherford model, and we also discussed about the limitations of Rutherford model, right. Now in today's class we are going to discuss first very important thing, that is developments leading to the Bohr's model, okay, and the next one we are going to discuss is the Bohr's model, okay. And in next class we will be discussing about the quantum model and the towards quantum model and quantum model, okay. So now coming to year wise weightage, you can see continuously one question from this chapter is a must. So sorry, this is part 2 here. So in this, now what is this development leading to Bohr's model? See here, like how Rutherford did gold foil experiment to get conclusion about the model of the atom, right. So similarly Bohr, when he was developing, or when he thought to develop the atomic model, so before that some scientific advances took, okay, some scientific observations were found out, and from these observations or from these results Bohr took his idea and then he improved his model of atom, or he proposed his model of atom. But he took the idea from two important developments that took place in science, okay. So that we will be seeing what are these two important developments, and under that we will be seeing wave nature, particle nature, quantized energy levels. So everything we will be discussing in detail here, okay. And next we will be discussing about Bohr's model, where we will be talking about Bohr's postulates and the limitations of Bohr's model, okay. So now coming to the first thing, that is development leading to Bohr's model. This is very important. So you can see here, okay. So what were the two important developments? The first one is the dual nature of electromagnetic radiation, okay. So by this time, or before Bohr gave his atomic model, it was well established about the dual nature of electromagnetic radiation. Now what is this dual nature? So under this we will understand that electromagnetic radiations have both wave nature and particle nature, okay. And the next important development that took place was atomic spectra of hydrogen, okay. So we were able to understand the atomic spectra of hydrogen, and in that we will be studying about the line spectra of hydrogen, and we'll be understanding about the emission and absorption spectra. Will not go much in detail about this, but yes, we'll have a brief discussion about this, okay. So next coming to so what is the first thing that we are talking about? Electromagnetic radiation. Now what is electromagnetic radiation and what is this dual nature? Okay, let us understand this in detail. So first, I hope this is clear. What is the chronology here? Before the development, or before Bohr proposed his atomic model, two important developments took place. The first one was the dual nature of electromagnetic radiation, and the second one was the atomic spectra of hydrogen, okay. So now what were these developments? We will understand in detail. So the first development was we'll talk about this. The first development here was wave nature, okay. So now you can see here, when electrically charged particles move under acceleration, alternating electrical and magnetic fields are produced and transmitted, okay. So whenever there is any electrical charge, okay, and it is in a magnetic field, okay, whenever there is an electrically charged particle under acceleration, okay, if a electrically charged particle is under acceleration, then it will emit radiations, okay. So that is what is called as your electromagnetic radiation. Now one more important thing here, what we should consider here is light waves are associated with oscillating electric and magnetic field. Okay, so first of all, let us understand what is this electromagnetic radiation. Okay, so electromagnetic radiation is nothing but a way to transfer energy. Okay, so electromagnetic radiation is a way to transfer energy. Okay, like suppose for example, you want to transfer letters. Okay, we have the medium is post office, right? Similarly, you just think that if you want to transfer energy from one place to another, then which is that carrier that can do that, or which is the medium, or which is the source from which we can do it? So that is your electromagnetic radiation. Okay, now if you see some properties of electromagnetic radiation, as the name suggests, okay, so in this electromagnetic radiations there are both electric field and magnetic field, and these electric field and magnetic field are perpendicular to each other. You can see if this is the electrical field, this is the magnetic field, right? They are perpendicular to each other, first thing. Okay, now second thing, you can know that for the transmission of this electromagnetic radiations, no medium is required. Okay, we do not need any medium here. Okay, it can transfer, it can even move in the, it can even propagate in the vacuum. Okay, so we are talking about now electromagnetic radiation. Now this electromagnetic radiation has some properties of a wave. Okay, so what are these properties? So we have three important terms here, that is wavelength, okay, next frequency, okay, these two, wavelength and frequency. Now you see, what is this wavelength? We do not have to know definition and all for KCET, we just need to understand what is wavelength. So wavelength I can define in this way, so I'll write it here. Yeah, so I can write here, wavelength is the distance between, okay, distance between crest or trough or crest and trough. Now what is this? See here, if this in a wave, if you see the one which is going down, okay, this is called as trough and this is called as crest. Okay, so the distance between two crests, these are two crests, so this distance can be called as wavelength or lambda, or you can take it as two trough, okay, this trough and this trough. Okay, so this distance is also can be called like this distance to this distance, that is also wavelength, or you can consider one crest and one trough, so this distance can also be called as wavelength. Okay, so wavelength is the distance between two crest, two trough, or one crest and one trough. Okay, so that crest and trough, if you are taking, it should all be in adjacent way. Like suppose if I see here, okay, so this is suppose a wave I am doing. Okay, now this is the crest, this is the crest, so this distance is called as lambda. This is the trough, this is the trough, this is also called as lambda, or this distance, one crest and one trough, is also lambda. Okay, wavelength. Clear? Now the next thing is about the frequency. Okay, what is frequency? So frequency is denoted by the shape nu, and it is the number of cycles per second. Okay, now what is this number of cycles? See here, if you complete one crest and one trough, okay, this is one cycle, then one crest, one trough, this is one cycle. Okay, so now what happens? We have a boundary like this, if you see, then in suppose this one wave completes this much distance in 1 second, then how many cycles have been completed here? 2 cycles are completed, right? So that means I can say that the frequency of this wave is 2. Okay, 2 cycles completed per second. Okay, clear this one? Now there is a relation between, so okay, one more thing is this electromagnetic radiations travel with the speed of light. Travel with the speed of light. Okay, travel with the speed of light. Got it? Fine. Now we will discover, we have a relation between, so the speed of light is denoted as c. Okay, so we have a relation between lambda, nu and c. Okay, so what is that relation? So this relation I have, sorry, written wrong. I will correct it. 1 second. Okay, so we'll make a new formula here. C is equal to lambda into nu. Okay, this is the important formula that you need to keep in mind. Okay, please cut this formula, this is not required. C is equal to lambda into nu. I hope you are getting this one. So what we have talked till now, we are talking about the developments that took place before the Bohr gave his model. So the first development was the dual nature of electromagnetic radiation. Now to understand what is dual nature of electromagnetic radiation, we need to first understand what is an electromagnetic radiation. Okay, so electromagnetic radiations are the radiations, or we can say is a form of transforming energy, and it generally has this wave like properties. Okay, so what I can conclude here is, see here, electromagnetic radiations are waves. Okay, this was known from before. Okay, means scientists already have discovered this one, that these radiations are having wave nature. So what was the thing that was given new, and that was the particle nature of electromagnetic radiations. Okay, so scientist was like completely unaware about the particle nature of radiations. They were only knowing about the wave nature of electromagnetic radiation. Now if they came to know about particle nature, okay, this particle nature was still hidden. Okay, nobody knew about it, nobody discovered it, nothing was, that idea was only very new to the scientists. But how can you think about something which is so weird? Okay, so for thinking that something should have happened, some experiments would have been done, right? Something or some observations might have been done which led or which forced the scientists to think that even radiations can have particle nature. Okay, so now what, when we think about radiation, our brain will imagine it as a wave. Okay, because we have been seeing radiations have wave properties. Okay, but there were two important, I can say, observations, experiments or something which led to the particle nature of radiation, and those two were your black body and photoelectric effect. Are you getting this all? Once again I'll repeat the story. Now we are discussing about some developments that took in science before Bohr proposed his model. So we all knew from before, all the scientists knew from before, that electromagnetic radiations are wave like, they are some things, or they are some wave, they have wave properties, they have frequency, wavelength, they have like they can travel in the vacuum. Okay, that is all known about wave, and these are all that was known for electromagnetic radiation. Now something which was undiscovered was the particle nature of electromagnetic radiation, and this discovery took with two important experiments, or you can say two important observations, that is black body and photoelectric effect. Okay, so we'll understand them in little detail. So we'll go to first now. Okay, one more thing here about electromagnetic radiation. So these radiations are of different wavelengths and different energies, and this series of electromagnetic radiations is called as electromagnetic spectrum. Okay, so you can see here the spectrum, like we have radio waves to gamma rays. Okay, so we have radio waves are the one which is having the very less energy. Okay, and so we have one more formula here, we'll write about the energy. So that is see, E is equal to hc by lambda. Okay, or I can say this is about, okay, we'll talk about this formula little later. Okay, we'll talk about this after some time. Okay, once we discuss about the particle nature, we'll discuss this. So for now, just leave it. Okay, so now what I was saying, what is this electromagnetic spectrum? So electromagnetic radiations are of different wavelength and different frequencies. So this collection of all type of electromagnetic radiations are called electromagnetic spectrum. Okay, so what type of spectrums are, so these spectrums are divided into radio waves, microwaves, infrared, UV, X-ray and gamma. Okay, so you have to remember that radio waves, okay, radio waves have low energy, okay, and the gamma rays have high energy, okay, low energy to high energy, and these radiations are not visible to human eyes. There is one reason, that is, like for example, first is radio waves, then microwaves, infrared rays, then you have visible, okay, sorry I forgot this, visible, then UV, then X-ray, and then gamma, right? So this visible region is the only electromagnetic radiations which the human eye or UV as humans can detect, okay. So what is electromagnetic spectrum? It is clear, okay. Now let us go to the particle nature. This was something which blew scientists' mind. This is something very new concept that the scientists came to know. So I told you there were two important events that gave the idea of particle nature of the electromagnetic radiation. Those were black body and photoelectric effect. So first we will discuss about black body. Okay, so now what is black body? So if you just define black body, any ideal body which emits and absorbs, okay, which can emit and absorb radiations of all frequencies uniformly is called a black body, and a radiation emitted by such body is called as black body radiation, okay. So what is that? Any body which can absorb all types of radiations, means all frequency. You saw electromagnetic spectrum, right? Different radiations are there of different frequencies. So any body which can accept or which can absorb all types of radiations and can emit all types of radiations are called as black body, okay. So now intensities of radiations of different wavelengths emitted by hot body depends upon its temperature. So what happens, suppose a body is there, okay, and you are heating it continuously. So slowly what will happen, it will become heat and it will start emitting radiations, okay. So which the intensity of this radiation, okay, the intensities of radiations of different wavelengths emitted by this black body. So what is the wavelength of this emitted radiation and what is the intensity of this emitted radiation? That depends on what temperature this body is heated. Are you getting what I am saying? Any body which can emit radiations of different frequencies, of all types of frequencies, is called as black body, right? Now if this, like, so at a particular temperature it emits lights of, or it emit radiations of a particular wavelength, okay. So what will be, like, what factor depends, like what radiation will be emitted? So that is the temperature at which the body is heated, okay. Next, so now what we observed, what should be the general observation here? See, if temperature increases, the energy, I can say the wavelength of the emitted radiation, temperature increases, then the wavelength of emitted radiation increases, okay. And that means we can consider that energy of emitted radiation should also increase, right? Now see here, the energy emitted by the black body should increase dramatically. In fact, it is suggested that at very short wavelength the black body would emit an infinite amount of energy. So that is what is saying, if you are like keeping the body and it is emitting radiations of different intensities, it is giving any intensities it can give, then the energy released from this black body will also be very high, okay. So just listen here, we are having this body, okay. See it very clearly, two things are there, two things that may confuse you, that is wavelength and intensity, okay, and another is energy, okay. Two important keywords are here. Now what I am saying, when a body is heated at a particular temperature, it emits radiations, one second, yeah, so it emits radiations, okay, of a particular intensity and wavelength, okay, of a particular intensity and wavelength. Now from this radiations which is emitted, we can calculate how much energy is released, okay. So from this wavelength what we can calculate? We can calculate the energy released, Okay, the energy released can be calculated. Now if we know that if we heat this body to a higher temperature, then this wavelength, like the intensity is increasing, okay, and so that is why if intensity is increasing, more like energy, so that means the energy emitted by the body should also be very high, okay. The energy that is emitted, that is produced from this radiations, okay, this radiations can be used to calculate the energy, okay. So now this radiations energy can be calculated, and that can be very, very high, because if you heat this to a very high temperature, it will emit high intensity radiations and high in energy can be released. That is what was expected about this black body radiations. So now let us understand what exactly was happening, okay. This is what was expected, that if you increase the temperature, high intensity radiations will be emitted, and from that we can get huge amount of energy indefinitely, right. Now what is the reality is like this. See, at a given temperature, okay, at a given temperature the intensity of radiation emitted increases with the increase of wavelength, okay. So as the wavelength keeps on increasing, the intensity also keeps on increasing, reaches a maximum value at a given temperature, and then starts decreasing with further increase of wavelength, okay. So now here we can relate that the energy was not increasing continuously as it was expected. So energy and intensity are similar terms, okay. If energy will be high, intensity will also be high. So we can say that the intensity will be like indefinite. But what it was observed, that the intensity first increased, reached a maximum value, and then started to decrease, okay. So now what was this is something which was not expected by the scientist. What did the scientist expect? That the intensities keep on increasing, okay, but that was not happening. It increased to a certain value and then start falling down, okay. Then what was the reason for this? How was this problem solved? Okay, so this problem was solved by a very good theory given by Max Planck, okay. So to solve this, Max Planck proposed a new idea, and he suggested that energy could only be emitted or absorbed in discrete packets or quanta, okay. So he said that energy, you cannot just release whatever energy you want. Energy can be released in only discrete amounts, okay. Certain amounts only energy can be released. Indefinite energy cannot be released, okay. He said that, and he gave a term that this quantized, okay. Now what he said that, so energy, if you want to give, this energy can be released in the form of packets, okay, and these packets of energy are called as quantum, okay. And what is the energy of each quantum? How to find out? E is equal to h nu, okay. Now what is E is equal to h nu? Here h is Planck's constant, okay, based on the scientist who discovered, and its value is 6.63 into 10 to the power of minus 34 joules second, okay. This is Planck's constant. And what is nu value? Nu is your frequency here, okay, and frequency units is second inverse. This is done. Next, what is there? That E is equal to h nu. Now we can write this expression by little modification. So if you remember, we have this relation, right? C is equal to lambda into nu. So now if I want to write nu, then that will be C by lambda. So we will get C by lambda, okay. This expression will also be derived from here. Getting? What does Planck said? That you cannot release energy in this way. Energy can only be released in the packets. Each packet of energy is called as quantum, and how to calculate the energy of each quantum? The formula is like this, okay. Now this quantized approach explained why energy didn't blow up at short wavelengths. Only certain amounts of energy could be emitted at high frequencies, okay. So that is what the energy cannot be indefinite. It can only be released in certain packets or certain discrete amounts, and that is why there will be no infinite energy prediction, okay. So next, coming to another, so I told you there were two events which help to understand the particle nature of wave or particle nature of electromagnetic radiations. Okay, so the first one was your black body radiation and second was the photoelectric effect. Okay, so this one you will be able to understand more easily. So what does this photoelectric effect tells? That if any light is there, okay, yeah. So you can see this is a metal sheet, okay, this is a metal sheet, and if any light radiation or in any radiation falls on this one, then electrons can be ejected out from this metals. Okay, clear? So now why can't the wave nature of electromagnetic radiation explain this? So there are some points that you need to understand. What is my question here? Why can't the wave nature of electromagnetic radiation why can't the wave nature of electromagnetic radiation explain photoelectric effect? I'm just writing PE. Okay, now understand, we'll not like just understand this one. Suppose this is a metal sheet, okay, and you are giving energy, we are believing that the radiations are in the form of waves. Okay, so now I told you that there were two events that led to the discovery of particle nature of electromagnetic radiation. The first one was black body, which we discussed in detail. Now the second event which led to the discovery of particle nature of electromagnetic radiation is your photoelectric effect. Now first here we will understand what is photoelectric effect, then we will understand why the wave nature cannot explain the photoelectric effect, and then we will discuss the formula of photoelectric effect. Okay, so first let us see what is photoelectric effect. Okay, I am not going to write any definitions and all, we will just understand this. Okay, so what happens is when a metal surface, okay, you have a metal surface, and when you strike a metal surface with the light, okay, when you strike a metal surface or when a metal surface is struck with the light radiations, okay, electrons are ejected out from this metal surface. Okay, that is called as photoelectric effect. Okay, so whenever a radiation is striking a metal surface, electrons are ejected out. That is called as photoelectric effect. Okay, now what is the observation? So this experiment was done, and what were the observations here? That should be very, very clear. The first thing was okay, so what was the first observation here? No time lag. That means whenever this light, okay, light hit the metal surface, immediately the electrons were ejected out. There was no time lag in between there. So when the light hit the metal surface, immediately electrons were ejected out. Okay, that was the first observation. Now what was the second observation here? The second observation was if the intensity of the light increased, okay, number of ejected electrons increased. Okay, if you increase the intensity, okay, if the light intensity means bright light and dull light. Okay, so if the intensity of the light was increased, then the number of electrons ejected were definitely more, but their energy, but the energy was the energy of electrons dependent on the frequency of light. Okay, so when you increase the intensity, what happened? Number of electrons ejected were more. Okay, but there was no change in the energy of the ejected electron. But if you increase the frequency of the light, then the energy of these ejected electrons were also increased. And the third and the most important thing is your threshold frequency. What does this threshold frequency tell you? That you can emit light of any radiation, but there is one minimum frequency. Okay, there should be some minimum frequency. So this frequency, if your light frequency is more than this minimum frequency called as threshold frequency, then only the electrons will be ejected out. Right, what is the point I am saying? if the frequency of the radiation is more than this minimum frequency, that is the threshold frequency, then only the electrons will be ejected out. Okay, so you can give any intention like any intensity radiation, okay, but the frequency of that radiation, if it is less than this threshold frequency, then no electrons will be ejected out. Okay, so now if we see the formula for this photoelectric effect, so it is like this. I'll clear here, one second. Yeah, so this h nu, okay, see this nu is what? Nu is the frequency of the radiation. Okay, we have just seen E is equal to h nu. So h nu is the energy of the radiation, and how is that energy of the radiation utilized here? So sum of it will be equal to h nu 0. Now what is this h nu 0? The minimum energy required to remove the electron. Okay, this is called as threshold energy. Okay, and then whatever the rest energy is left, with that kinetic energy the electron will move. Okay, now for example, let us take a very simple example. Suppose you have here, one second, I'll explain here. See, suppose you have a nucleus here, okay, electron is here, and you are ejecting a light, okay, a radiation, and this is the threshold frequency, the minimum energy that is required to remove the electron. Okay, so let that be 2. Okay, just I'm taking a number 2, and you have given a the energy of this radiation is 10. Okay, so now what will happen? First this electron will come out, right? For that, out of this 10, how much will be utilized? 2 energy will be utilized, 2 units of energy will be utilized. Now what is the rest energy that is there? 8 units. So this electron will move after coming out with a unit of 8 energy. Okay, so that is why I can say the total energy of the radiation, total energy of radiation, okay, will be equal to or will be utilized in the threshold energy, okay, plus kinetic energy of electrons. Okay, so now what is this total energy of radiation? That is h nu. Okay, total energy of radiation is h nu. Now threshold energy is h nu 0, and this is half mv square, or we can write it like E equal to E naught plus half mv square. Clear? Got it, this one? Okay, now we will move to the, so we told, so that I told you that there were like 2 important developments that gave idea to Bohr regarding the his atomic model, right? The first one was dual nature of electromagnetic radiation. Under that we understood what is wave nature and what is the particle nature, and particle nature was given by 2 important events again, that is black body radiation and photoelectric effect. Now the second thing which was which was a development that led to the Bohr's model was your atomic spectra. Okay, so what is this atomic spectra? So so here first of all we should know that the atomic spectra of hydrogen, okay, was discontinuous. Okay, so generally if you have done the experiment of refraction and you have passed a white light through a prism, you would have seen a spectrum, and this spectrum would be continuous, right? The light, it will change from violet to red in a continuous manner. But if you do if you take hydrogen and observe its spectra, then it was very discontinuous. You find lines somewhere and you find lines, somewhere the lines were missing. Okay, so that is what the hydrogen spectra is, discontinuous. And in hydrogen what happens? See, there are different energy levels, N1, N2, N3, N4. Okay, so when you suppose electron is present here, okay, electron is present here. Now when you give energy to this electrons, okay, it can go like how much energy it is absorbing. Based on that it can go either to this level or to this level or to this level, like this. Okay, so it cannot go somewhere here. Okay, there is no energy level here. So whenever this electron gets the energy, it should get approximately that much so that it can reach here. Okay, so that, and when it comes down, it will come, when it releases energy, it will come down, and that time it will emit some radiation, and that is what we see in the spectrum. Okay, so how to calculate this energy transitions? So here is a formula, here is a spectral series of hydrogen, that is Lyman, Balmer, Paschen, Brackett and P1. Okay, so now in Lyman series, what is the meaning? So the electrons is coming back from any higher level to the first level. Okay, so and in Balmer series to the second level, third level, fourth level and fifth level. Okay, and this energy transition lies in the ultraviolet region, this is in the visible region, and these are in the infrared region. What is the meaning of this? Means the energy that is released, okay, that wavelength of energy comes in this area. Okay, now how to calculate? Here we have formula 10967 into 1 by n1 square minus 1 by n2 square. We will do a question, like when you do question it will be more clear. So what is here n1? So you should remember here that n1 should be less than n2. Okay, sorry, yeah, n1 should be less than n2. Okay, so 10967 1 by n1 square minus 1 by n2 square. Okay. Now coming to the next topic, that is Bohr's model. So based on these two experiments or these two I can say developments that took place, Bohr finally proposed his model of atom, and in the first he said that the stationary states for electrons are numbered 1, 2, 3. These integral numbers are known as the principal quantum numbers. So he said that we have a nucleus and we have these stationary orbits. Okay, stationary orbits on which the electrons revolve. Okay, but the point here is the energy of this stationary orbit is fixed. Okay, the energy is fixed, the energy of these orbits are fixed, and electrons rotate or revolve around these orbits only. Okay, next point, we can calculate the radius of this orbit. There is a formula, the formula is Rn is equal to A naught into n square. This A naught value is 52.9 picometer. Okay, next we can also calculate the energy of this orbit. So I told you every orbit is having a fixed amount of energy, so the energy is like minus RH by 1 by n square, where RH is your what called as Rydberg constant. Okay, and what is the value of RH here? So RH value here is minus 2.18 into 10 to the power of minus 18 joules. Okay, clear? Fine. Next is if it is a hydrogen like species. Now what is the meaning of hydrogen like species? Number of electrons should be 1. Okay, like for example, if you have helium 2 plus, okay, in that case helium 2 plus will have only 1 electron, so that is a hydrogen like atom. Okay, so if any hydrogen like atoms are present, then we can use the same formula but with little modification. So we need to introduce this Z term, where Z is your atomic number. Okay, so our formula, our value is 52.9 n square by Z. If you remember the previous value, if you want to calculate only for hydrogen, then it is 52.9 n square. But if it is for any other element but they have also 1 electron, then it is 52.9 n square by Z. Okay, now if we we can also calculate the energy of this, and En will be equal to minus 1 RH Z square by n square. Okay, this formula is for energy. Next we have electrons absorb and emit a fixed amount of energy to jump up or down the energy levels. Okay, so electrons cannot accept any energy, they can accept only a fixed amount of energy to go to the higher level, or they can release a fixed amount of energy to come to the lower level. Okay, so here is the postulates given by the Bohr's model. Okay, So now what is the limitations of Bohr's model? So the limitations here are it accounts to fail for the finer details. Okay, sometimes we can find that in the hydrogen spectrum, apart from these lines, there are other small lines, okay, which could not be defined by the Bohr's model. Next, the hydrogen spectra splitted in the field of electric and magnetic fields. Why was that happening? That was also not explained by the Bohr's model. It could not explain the ability of the atom to form molecules by chemical bonds. Okay, so yes, these were the limitations. Now we will go and solve some questions from here. Okay, this was the homework question that I gave you. The ratio of neutrons in carbon and silicon with respective atomic masses of 12 and 28 are. So we have carbon and nitrogen, silicon, right? Okay, silicon. So here we have number of electrons as 6 and here 14. Then we have number of protons. Okay, so protons will be again same, electrons and protons are same. If I calculate number of neutrons, okay, neutrons will be this minus this, so this is 6 here and this is 28 minus 14, that is 14, right? So I need to take a ratio of this one, that is 6 by 14, so that is 3 by 7. Okay, so I'll get option number C here. Hope you all have done it correct. Okay, next, with regard to photoelectric effect, identify the correct statement among the following. Okay, so this was asked in 2020. Okay, the number of electrons ejected increases with the increase in the frequency of incident light. No, the number of electrons depends on the intensity of the light. Okay, so number of electrons ejected increases with the increase in work function. Now what is this work function? So work function is nothing but, okay, I'll write here, the threshold energy. Okay, threshold energy is equal to work function. Okay, next, the number of electrons ejected increases with the increase in the intensity of the incident light. Yes, this is correct. Number of electrons ejected increases with the increase in the intensity of the incident light. Okay, next question, the energy of the electron in the nth Bohr orbit of the hydrogen atom is. So here we have seen that the energy formula I have shown you was minus RH into z square by n square, right? Or we need not write for z for hydrogen, by n square joules. Okay, now this RH value was minus 2.18 into 10 to the power of minus 18 joules. Now if you want to calculate in terms of EV, then this RH value is minus 13.6 EV. Okay, so that is why I can put minus 13.6 by n square, option number A. Okay. Okay, next, what is the ratio of the atomic radius of the 5th orbit in chlorine atom and 3rd orbit in helium atom? Okay, so we have chlorine atom 5th orbit and we have helium atom and 3rd orbit, right? So if you remember, radius formula is what? A naught n square by z. Okay, so if I want to calculate the radius of first chlorine, okay, so A naught value should be like this. Which orbit is asked here? 5th orbit, so 5 square. Z value is how much here? For chlorine, the Z value is 17. Okay, next if I want to calculate for helium, right? So helium is A naught again. N square value here is 3rd orbit, so that means 3 square. Z value is 4, right? So it is 25 by 17 and we have 9 by 4. Okay, so if I take a ratio of these two, I'll get 25 by 17 divided by 9 by 4 and that can become, right, 4 by 9. Okay, so if you see, we will get, one second, we can check the calculation once again. 25 by 7, it is asked for chlorine and helium, right? Yeah, 25 by 7 by 9 by 4 by 4 by 9. So we should get this one as 100 by 153, right? Option number D. Once again, let me check the calculation. A square n square by z. So we have 5 square by 17, 25 by 17, and here it is n square, yeah, third square by z, 9 by 4, 25 by 17 by 9 by 4, so it will become 4 by 9, yeah, 100 by 153, option number D here. Okay. Okay, next, what is the order of the radius of an electron in the hydrogen atom? Okay, so the order is generally in the form of 10 to the power of minus 11. Okay, option number C here. Okay, next, hydrogen atoms are excited from ground state to the state of principal quantum number of 4. Okay, so that means it is saying that we have hydrogen levels like this: n equal to 0, n equal to 1, n equal to 2, n equal to 3, and n equal to 4. Okay, so one electron was emitted and was excited from here to here. Now when it comes down, how many lines it can produce? Okay, so to calculate, you can do like, what the meaning is, it can come here, okay, it can come here, it can come here, it can come here, right? So sorry, there is no n equal to 0, I'm sorry, here it is n equal to 1. Okay, so 1 second, yeah, n equal to 1, 2, 3, and this one I can erase, or let me erase everything, wait. Okay, the question is asking you, hydrogen atoms are excited from ground state to the state of principal quantum number 4, then what will be the number of spectral lines? Yeah, so we have here like first level is 1, then we have 2, then we have 3, and then we have 4. Okay, so one electron is there, it is excited to the 4th level. Okay, now when it returns, it can have a lot of lines possible. What are they? Okay, so now the formula to calculate here is n into n minus 1 divided by 2. Okay, so what is the value of n? We have 4 here. Okay, then 4 minus 1 is 3, and then we have 2 here, so it will give you total 6 lines. Okay, that is option number B. So you need to remember this particular formula. Okay, so this is a homework question. What will be the longest wavelength in the Balmer series of hydrogen spectrum? Okay, I'll give you some hint here. See here, longest wavelength in the Balmer series of hydrogen spectrum. So Balmer series means what? If you see here, n equal to 1, we have n equal to 2, and like this we have so many energy levels, right? Now Balmer series means it should come down to n equal to 2. Okay, from any level it should come to n is equal to 2. Now it is asking for the longest wavelength. Okay, now if you see, energy formula is what? Hc by lambda. If the wavelength should be longest, then the energy should be very small. Okay, inversely proportional. Then which transition will have the least energy? The transition which is taking from n is equal to 3 to n is equal to 2. This transition will have least energy and longest wavelength. So now if you want to calculate the wavelength, the formula is like this. We have seen, that is I'll tell you. Yeah, so the hydrogen spectra formula, what we did was 109677 into 1 by n1 square, right? So n equal to 2 and 3. So I told you n1 should be smaller than this. So 1 by 2 square minus 1 by 3 square, okay, centimeter inverse. Now this value, or this is nothing as 1 by lambda. So just calculate this and then reverse it, and then you can get the answer here. Okay, after that you can comment the answer. So yes students, this was all about the part 2 of structure of atom. Next part will be completing this chapter. Hope you are finding it useful, and please subscribe the channel, and if you are liking this KCET series, and do not forget your target. Okay, see you soon in the next class.